Thanks for coming, folks. We're running a little short on time, so I'm going to speed through a couple of these slides. I hope you'll forgive me for doing so. If I actually know how to use this. Press the green button. Okay, cool. So I don't think I have to really give you the whole spiel about complex mixtures. Everybody here probably understands that exposures always occur as complex mixtures. PM 2.5 is just a complex mixture of different chemicals, and it varies depending on where you are. Day-to-day consumer projects that we use expose us to many different compounds. So a particular class of interest is endocrine disrupting compounds. They're kind of a quintessential example of a complex mixture problem. They've been defined as substances in our environment, food and consumer products that interfere with hormone biosynthesis, metabolism, or action resulting in a deviation from normal homeostatic control or reproduction. Everyone in this room is exposed to endocrine disrupting compounds. Just depends on how much. They've been shown to cross the placenta and thus may impact childhood neurodevelopment via a number of different pathways that disrupt normal hormone development. One study found that in serum samples from pregnant mothers, this is from the NHANES data, there were at least 25 distinct endocrine disrupting compounds that were detectable in blood. So while it's believed that endocrine disrupting compounds may impact neurodevelopment during fetal growth, it is not clear which compounds are the so-called bad actors, which ones we should be concerned about. It's very reasonable that some are worse than others. Evidence has implicated chemical classes and maybe specific chemicals within classes, but the results are not consistent. One reason this might be the case is multiple comparisons problems. Multiple comparisons is a testing problem where we identify an effect that doesn't actually exist, and we identify it just because of the nature of statistics. And the more tests you conduct in a data set, the more likely you are to find a result that seems interesting but is actually just a result of statistical noise. One way around this is to use Bayesian methods. Now, when I say that Bayesian methods handle multiple comparisons, they actually just don't do any comparisons, so to speak. They completely reframe the way that we do work from being interested in testing to being interested in estimation. So it's a little bit of a cheat in getting around multiple comparisons. But analytically, the more interesting part of this is that they can handle multiple correlated data so that we can consider all these exposures that are highly correlated within a single regression framework with the use of priors. So if you took my short course yesterday, thank you, it was awesome. And if you didn't, sorry, it was awesome. This is a slide that I always use, and I will use it until the end of time, to just illustrate how Bayesian methods work. So the likelihood is actually not the likelihood there. It's the probability of the data given parameters of the model of that you're using, and it's proportional to the likelihood. So it's basically a really good estimation of the likelihood. The P of A is the prior, and that's the really interesting Bayes part. The PB on the bottom, we just basically ignore. It's the probability of the data, and we just take the data as a given. So the prior is the part that's very helpful to us, and as you can see, what you get from a Bayesian model on the left side of the equation, the posterior, is just a product of the likelihood approximation and the prior. So the research question I want to ask is, can we identify independent effects of endocrine disrupting compounds that occur as a mixture with autism spectrum disorder or intellectual disability? So I explored this in the early markers of autism cohort. Briefly, participant mothers were enrolled in California's expanded alpha-fetoprotein prenatal screening program between 2000 and 2003. And participant mothers were required to have given prenatal blood samples between the weeks of, between gestational weeks 15 and 20 that were stored. They were later followed up, and children were identified as having autism spectrum disorder or intellectual disability based on California Department of Developmental Services records. And for ID specifically, an IQ of less than 70 was the cut point. ASD cases were ascertained from those records, and then they were further confirmed by expert clinician review. In total, I had 545 ASD cases and 181 intellectual disability cases. And ASD cases or general population controls were matched to ASD cases in this work based on the sex of the child and the child's birth month and year. So we had 418 controls to work with. The exposure assessment was endocrine disrupting compounds that were able to be measured in maternal blood between 15 and 20 weeks of pregnancy. We restricted the exposures of interest in this case to those that had greater than 60% of all samples above the limit of detection. I put the 25 chemicals that we included there in a list. I don't expect you to actually digest all of that, but it's 6 brominated flame retardants, 11 PCBs, 6 per and polyfluoroalkyl substances, and 2 organochlorine pesticides. So the way we model this is, of course, case versus control status for the outcome. The exposures I considered in 2 ways. One, we adjusted each exposure based on its Z-score standardization, so the change in effect is per 1 standard deviation change in exposure. And then we quartiled the exposures based on their distribution so that the second, third, and fourth quartile were compared to the first. The confounders are maternal age, education, race, ethnicity, and parity, and the child's birth sex and birth month year, of course, because we did matching to ASD cases for controls. We fit logistic regression models using 2 Bayesian priors. So I want to spend just a minute on this, or maybe 2 if I'm lucky. So we have 2 priors here, the shared mean prior and the mixture prior. So very briefly, the shared mean prior is an assumption that before I even conduct the analysis, I believe that all of the effects of exposure of the 25 chemicals I'm looking at overlap at least a little bit. It's called kind of partial exchangeability in this sense. So it's a little bit of a heavier assumption. So a more flexible prior is the mixture prior, which is not dissimilar, but it allows for multiple groups. So it's not saying that I believe that all the chemicals share a common effect. It's that probably more or less a lot of these compounds share effects that may be distinct from one another. So you can imagine that maybe 5 compounds will cluster into a null spiked group. They don't really have an impact on the outcome. And then maybe 5 are in a modest effect on the outcome group, and then another 5 are in a high effect on the outcome group. So that's kind of how that works. That specifying that prior allows the data to kind of explore those different effects, possibilities of effect on the outcome, and allows the data to decide which groups they're in. So that's kind of one of those things that gets lost in this, is that the data do really the heavy lifting here. So the priors are informative only to the extent that the data and the model really conform with them. So to give you a sense of what the correlations look like for the endocrine disrupting compounds, they cluster very heavily within their own classes. It's probably a little hard to see that here, but for example, on the lower left, those are the PBDEs, which the lighter color blue is high correlation, and then that big square in the center is the PCBs. So there's a lot of heavier correlations among those 2 groups, and less so in the brominated flame retardants, or the PFAS, I'm sorry. So I could have put a slide up here with 25 nearly null-centered point estimates, but I thought that would be silly. So I'm just going to go ahead and say that the results for the main effects of analysis were basically null. Every single point estimate on a table of 50 point estimates were either 1.0 or very, very close to 1.0, and all of them had credible intervals that overlapped that. So this was true regardless of the exposure parameterization I considered, regardless of the outcome I considered, and secondary analysis where I looked at just stratifying the data set based on the sex of the child resulted in nearly the exact same story, which is a really boring story, I'm sorry. So there were previous analyses of these data as well that considered all of these exposures. However, these analyses considered the exposures within single regression models. So each exposure was modeled independently of the others. And this is kind of where that multiple comparisons issue may arise. Associations were suggested for some PCBs in those previous analyses, and opposite effects were suggested for some PFAS based on sex, which may suggest sexual dimorphism, but for our analysis, we didn't really find any of that. So in terms of limitations, we did not have information on maternal BMI, which could be a strong confounder. We're not sure, so we couldn't adjust for it. And we did not explore the possible influence of other endocrine disrupting compounds that were below our limit of detection criteria cut point. Our strengths were that we had a relatively large sample size, biospecimens were collected prospectively during critical windows of neurodevelopment, and we used Bayesian methods, which I peddle to everybody I talk to. So this can kind of handle those multiple comparisons issues, handle multiple correlated exposures within single regression models. And I'm happy to field questions, which I think I have 20 seconds to do. Thank you.